What's up, everybody? So here are the solutions for week 10 worksheet, and for the first problem I'm asking you to compute three limits, but I specifically asked you to not use L'Hopital's rule, right? Of course these could be very easily done with L'Hopital's, but I wanted you to recall this special limit that we've been using quite a lot in our class, right? The limit as theta go to 0 of sine of theta over theta equals 1. So we'll be trying to use this to compute the following limits. For the first one, ideally I would like to have 1 over x in the denominator, so that I have sine of 1 over x over 1 over x. And the way to do that is by rewriting the problem as instead of root x, I'm going to write it as x over root x, sine 1 over x. So just copy that part down, and now I can bring this x in the denominator and it's going to look just like 1 over x. So now this is the limit as x goes to infinity of 1 over square root, that stays, sine 1 over x divided by 1 over x, the reciprocal of this x. And as x goes to infinity, this quantity 1 over x goes to 0, so I get to use my special limit, right? That means that this whole box is going to approach 1. So that means the whole limit is going to be just the limit as x goes to infinity of 1 over root x times 1. But I have a root x in the denominator that goes to infinity, so that means this whole limit goes to 0. That's our final answer. Now for the second problem, I don't have sine anymore, I have tangent, but I know how to express tangent in terms of sine and cosine, so that's what I'm going to do. Right, I'm going to write this as the limit of x times sine x over cosine, sine 1 over x over cosine 1 over x, and then I'll use the same trick to get a 1 over x in the denominator to match what I have inside the sine function. So this is the same as the limit of sine 1 over x divided by 1 over x, which I get by bringing this x in the denominator, times I'm left with 1 over cosine 1 over x. And this limit is as x goes to infinity, so 1 over x goes to 0. I get to use the fact that this whole thing now approaches 1, and cosine of 0 also goes to 1, so this whole limit should be 1. Now for the last problem, I no longer have an extra x to play with to bring in the denominator, and I also have, if I split up this tangent as sine of x, so then this limit is going to be just the limit of sine 4x divided by sine 5x times cosine 5x over 1, right? And these two guys show up from just the reciprocal of tangent. And now ideally I would like a 4x in the denominator and a 5x in the numerator so that I can use my special tool. So what I'm going to do is I'll rewrite this as the limit 4x times sine 4x over 4x, right? So I haven't changed anything, I just added 4x in the numerator and the denominator at the same time, times, I want a 5x in the numerator. I'll rewrite the sine 5x here, but because I added this here, I also need to divide by it, so I'll divide by it here, and I copy down the cosine part, cosine 5x, this part goes to 1, so does that. Cosine 5x, well, cosine of 0 is 1, so all of these three go to 1, and I'm just left with the limit of 4x over 5x, but if I cancel the x's, this is just going to be 4/5. That's our final answer. Now for problem 2, we are asked to sketch a function that satisfies the following conditions, so it's similar to the quiz problem. But I specify over here you don't necessarily have to make it continuous. Now, my solution for this sketch happened to be not a continuous function. I made that on purpose. Well, let's see what we get, right? So if I take a glance here, a couple of critical x values are 0 and 2. So let's put that up there. And also 4, where there's going to be some sort of concavity change. And I'm not given any y values for the function, so we can choose whatever. But I am given that the limit as x goes to infinity of my function is 0. So I have a horizontal asymptote at 0. So let's take a look. Let's give it a rough sketch here first. And if I look at the first derivative information, f prime of 0 is 1, so my function looks like this as it crosses 0, has a slope of 1, kind of like the y equals x. F prime of 2 is 0, so I have a min here, or a max, right? We don't know yet. F prime is decreasing for values greater than 2, so it's going to decrease after this. And it's increasing between 0 and 2, so this is indeed the correct picture. My function should look something like this. Now, in terms of concavity, let's see. It should be concave down between 0 and 4, and what I have here satisfies that. And it should be concave up past 4. So this is an inflection point, and if I make it concave up, keeping in mind that the limit at infinity is 0, this is that leveling off behavior. So let's go ahead and make a prettier looking sketch than this. So I'll start my function somewhere up here. I have to go up to what happens to be the max of the function. Then I continue with concave downwards. Now I have my inflection point at 4, and I level off just like so. Now there is one additional piece of information, which is that f of negative x is negative f of x, and that means I get to take this and I reflect it about the y-axis 180 degrees. So now I'm down here, so the reflection would look something like this. Boom. And actually I'm going to make these open circles, because the way I wrote this, f of 0 is going to be undefined. Now for the second part of the problem, we are asked, what would the graph of this look like if we require it to be continuous? And notice that discontinuity, the way I drew it, happens at 0. To make this continuous, I have to make f of 0 equals 0. So I have to have this point here. So if I redraw my graph, what that's going to look like is basically something like this. Right, where this peak happens at 2, this inflection point happens somewhere at 4, this value 4. I didn't quite draw it
up to scale, but you get the point. So that's the that's problem 2 and problem 3 all together. They're related to each other. So let's move on to problem 4. So what we have for problem 4 is I'm asked to sketch the graph of the given function. Right? So that means I have to take the first and second derivatives, figure out what are my critical and my inflection points, figure out any sort of concavity where it's increasing, decreasing, figure out if the function has any asymptotes, of course. So let's see what we get. So for the first part, what I'll do is I'll just look at the first derivative. So let's take the derivative of this. F prime of x is going to be negative 2x e to the minus x squared. That's just by chain rule. And to figure out the critical points, I set this equal to 0. And since the exponential is never 0, it's always a positive quantity, this is 0 only when x equals 0. Now, in general, there are other types of critical points, which is where the derivative would be undefined, but for this particular function, the derivative is defined everywhere for all real values of x. Let's also take a look at the second derivative here, f double prime of x, and I get to use product rule, right? I have a product of two functions, so this is going to be negative 2 e to the negative x squared minus 2x e to the negative x squared times negative 2x, again a derivative of my exponent from chain rule. And if I rewrite this a little bit, I'll factor out a negative 2 e to the negative x squared, and I'm left with 1 minus 2x squared, because I have an extra 2 here, and I have 2 x's. Now if I set this equal to 0, again the exponential part will not give me anything, will not give me any solutions. However, it is going to give me that I have 2 inflection points. X equals plus or minus square root of a half. If you set this equal to 0 and solve. Now let's see if these are actually inflection points. So I'm going to draw this little line for f prime. I get that this is going to be minus square root of a half, and this is going to be the positive part. And if I plug in 0, notice I get a negative quantity, so this is negative here. And now because this is not a double root, right, I get two distinct roots, that means f double prime has to change sign, so this automatically has to be positive here and here. I don't have to plug anything in, I just use the fact that this is a root of multiplicity 1, right? So if I actually were to factor this term, I get a linear factor to the first power and a linear factor to the first power that is different from the first. Let's do the same for f prime. So let's see where my function is increasing and decreasing. I only had one critical point of 0, and automatically if I plug in let's say a negative number here, I already have a negative sign here, so that's going to be positive for numbers less than 0, right? Because negative times a negative would give me positive. And if I plug in something positive, well, everything else is positive, but with this minus sign tacked on, I get something negative. So my function is increasing for negative values of x, decreasing for positive values of x. So now, can I get any other information about this function? Well, I can, because I know what e to the 0 is. So another piece of info is that f of 0 equals 0, I'm sorry, f of 0 equals 1, right? E to the 0 is 1. And also, if I take the limit as x goes to either plus or minus infinity of my function, well, I get e to the minus infinity in both cases, so that's 1 over e to the 1 over infinity. So this limit is going to be 0. So I get a horizontal asymptote both on the left and the right. And that should give me enough information to draw the graph of this. Right? If I put all this info together now, I'll draw a rough sketch over here first. So here are my two inflection points. I go from increasing and concave up. So I go from something that looks like this to increasing and concave down up until 0. Then I'm still increasing and then I get to be decreasing and concave down. So it looks like that, but then I get an inflection point decreasing concave up, just like so. So that's the rough shape of the graph, right, where these are kind of the cutoff values. So if I were to put this on the final sketch here, this is going to be plus square root of a half, this is going to be minus square root of a half. These are the inflection points. I have my horizontal asymptote, and I have my function starting up at 1. It looks like that. Inflection point, level off. Boom. Just like so. And notice this actually resembles the shape of a bell curve, and in fact this function is very closely related to the bell curve, to the normal distribution, to the density of the normal distribution. It's just off by like a factor of 1 over square root of 2 pi. So it's no coincidence that this has the shape of a bell curve. So let's move on to the second part of the problem, which has a slightly different function. This one is a little more complicated just because taking the derivatives gives you more terms and it's not as pretty to work with, but it should be approachable. So let's see. Again, what I'm going to do is I'll start by taking the first derivative. So I get e to the minus x squared, right? I have to use product rule, minus 2x squared e to the minus x squared. And this is because I have a negative 2x, derivative of the exponent, times the x that comes from right here. Okay, make this a little bit darker. There we go. So now if I set this equal to 0, I factor out the exponential part, I'm just left with 1 minus 2x squared equals 0, and this gives me two critical points, x equals plus and minus square roots again of a half, right, just like in the previous problem. And now I'll go ahead and I'll compute the second derivative, and this is going to be, let's see, for the first term it's just negative 2x e to the minus x squared, pretty simple, but now I have to use product rule for this one. So I get negative 4x e to the minus x squared, right, derivative of 2x squared here is minus 4x with that negative sign, and I copy down the exponential part, plus, now I get a 4x cubed because I pick up an extra x from the derivative of x squared here,
e to the minus x squared, and I have to set this equal to 0. But if I get rid of all the exponentials and I also divide by a negative, divide by a 2, not by a negative 2, just a positive 2, I'm left with this, this, and this. Just divide all of them by a factor of 2. So I'm left with 4x cubed. Actually, let's see. Yeah, don't divide by 2. Let's leave it like this for now. We'll divide by 2 a little bit later. Minus 6x. I don't want to do too many steps, then I'll get lost. Equals 0, right? So I have the highest power first. These are both x to the first. Combined gives you negative 6 equals 0. And this one I can factor very easily, but I'll divide by 2 at the same time. So I pull out an x, and I'm left with 2x squared minus 3 equals 0. So from here I get that x equals 0 is one of the potential candidates for being an inflection point. And from here I get that x is plus or minus root of 3/2. So I get 2 points from here plus 1 from here. I get 3 total candidates for inflection points. Let's look at the sign changes in the second derivative. So I've got 0 in the middle. I have the positive root 3/2, and I have the negative root 3/2. And I guess, let's see, we'll have to plug in something. And because I have the exponential part here, that's always positive. It's not going to change the sign, so I get to just plug it into this 4x cubed minus 6x. Right, and if I do that, what's a good number to plug in? Let's plug in, say, 1. Right, because 1 is going to be less than the square root of 3/2, which is 1.5. Right, so the square root of 1.5 is a little bit bigger than 1. So I plug in 1, I get 4 minus 6. That means it's negative in this region. But these are all roots with multiplicity 1, right? I don't have any double roots. So now I just get to alternate signs. I don't have to keep plugging in numbers for each little subinterval here. Let's do the same for my first derivative to figure out whether my function is increasing or decreasing. So I have 2 critical points, the negative root and the positive root, 1/2. And if I plug in just 0, automatically I get, this term is going to drop to 0. This is going to be just a positive number. And again, by the same argument as before, these are not double roots, right? These are just roots of order 1 or multiplicity 1, which is an odd multiplicity, so they alternate. Okay. Can I extract any more information? Well, automatically I can plug in 0 into f and compute it right away, so I have that f of 0 equals 0, and if I do L'Hopital's very quickly, I get that limit as x goes to plus or minus infinity of f of x. That's the limit as x goes to plus or minus infinity of, I'll bring the exponential in the denominator, so I have x over e to the x squared with a positive exponent now. And if I apply L'Hopital, I get 1 on top, and I get, again, an exponential on the bottom. So this limit has to be equal to 0. So I have a horizontal asymptote at 0, both on the left and the right of my graph. Now if I draw this out, what this is going to look like is basically, here, we'll have the critical points first. We'll have square root of 1/2. We'll have the inflection point. These are not,
there's no reason why these are equal, right, in terms of length. I have my asymptote here and here. I have have the negative root a half, which is a critical point. F of 0 is 0. I have my inflection point here.
And let's see what we can do. So, between 0 and here, I am concave down and increasing. So I look like this, and because I'm reaching a critical point here, I am going to level off. So that becomes a maximum. And then I start to decrease for a little bit, right, as I pass a half. So indeed, I stay concave down up to the critical point and decreasing. But then I continue to decrease by this, and I become concave up, and that's what gives me the leveling off behavior, right? This is the inflection point right here. Past it, I have to start leveling off to my asymptote, just like so. Now, if you look at the formula of the function, you notice that there is a, you notice that f of negative x basically is negative f of x, because I have this x multiplied here. So I can just quickly rotate this 180 degrees, or I could just use this information to complete the final part. But I'll go the quick way. I'll use the little shortcut. That's a min. Concavity changes here, and I start to level off to the asymptote. So that's the shape of the graph here. Okay, and that's it for the graphing problems. And last but not least, I have to compute a few limits, and these we're going to do using L'Hopital's. So for the first limit, I have ln of x over x, and as x goes to 0, the top goes to minus infinity, but the bottom goes to 0, so it's not quite the L'Hopital case, right? Instead, what I'll do is I'll look at this function as limit as x goes to 0 from the positive side, 1 over x times ln x, and now I just have two functions that are multiplied. So let's see what each of these pieces do, right? The function 1 over x, just from the positive side, looks like this, so it shoots up to plus infinity, and the natural log function shoots like that to negative infinity, right? So all I'm doing is I'm taking plus infinity times minus infinity. That is going to be a final answer of minus infinity. So no L'Hopital involved for the first problem. But for the second problem, we do need to start using it, right? Because notice, as x goes to 0, top goes to 0, the bottom goes to 0. So this is, by the 0 over 0 L'Hopital's case, same as the limit of, and now I have to take the derivative of the top, which uses product rule. So I get 3 to the x plus x, 3 to the x ln 3, divided by now 3 to the x ln 3, right, which is just the derivative of the denominator. So as x goes to 0, this goes to ln 3, top just goes to 1, because this whole term goes to 0 here, right, due to that factor of x. So this whole limit is going to be 1 over natural log 3. This next one, it's kind of similar to what we were computing the limit on the previous problem for the asymptote. What I'm going to do is I'm going to rewrite this as x cubed over e to the minus e to the positive x squared now. I keep writing this wrong. e to the x squared. And now this is just the L'Hopital infinity over infinity case, right? So this is where I take the derivative of the top, so I get 3x squared over 2x e to the x squared limit. And again, as x goes to infinity, top goes to infinity, bottom goes to infinity. So this again needs another application of L'Hopital's. But notice, as I keep taking the derivatives on the top, the power keeps dropping by 1, while at the same time the denominator will always continue to have some exponential term in it. Which means at some point, after actually 2 more applications of L'Hopital's, this is the same as the limit as x goes to infinity of a constant, in fact 6, over e to the x squared times something, times some polynomial. In x with a positive lead coefficient, right? Because I'm not getting any negative signs if I continue to take derivatives on the denominator. So the bottom has to go to infinity, which means this whole limit automatically is 0. Another way you could have seen this right away is you look at your original problem here and you realize, okay, exponential, right, just like we talked about in tutorial, exponential always dominates any polynomial to any power, so this denominator increases much faster than x cubed. In other words, the limit should go to 0, right? Now how about this last problem? This last problem is a little bit trickier, right? I can't quite turn this into a fraction right away to use L'Hopital's, so I have to use a little extra trick. Let's say that this limit exists, and let's call it L, right? If it exists, we're going to call it the number L. Our goal is to figure out what this L is. What I'm going to do is I'm going to raise e to both sides with
e to the L equals the limit of e to the x minus ln x, okay? Because e is a continuous, e to the x is a continuous function, so I can pass it inside the limit. But this is the same as the limit of e to the x divided by e to the ln x, which is just x, right? And as x goes to infinity, again, e to the x dominates x to the first, so this is the same, this whole limit is infinity. So I have e to the L approaches infinity, positive infinity, so the only way that can happen is if L itself is infinity. So this limit actually is infinity. And if you look at it, it turns out that any polynomial in x to any power, right, even square root or cube root or fifth root, always eventually grows larger than the natural log function, right? And I can draw a couple of graphs to show you this, right? If the power is an exponent larger than 1, it's going to look either like a straight line or like that, whereas the log looks like this, so automatically this dominates, right? X to the n dominates. But if it's a root, what will end up happening eventually is this will be the natural log coming in like this, and even if the root is small at first, it will eventually surpass the log, okay, and it will grow much faster. And to see that, you can look at the derivatives. right? And you compare them, and you'll see that this does indeed happen. Okay, so that's that limit. We just have two more. So the first, the second to last limit here is going to use a similar technique, right? If this limit exists, I'm going to call it L, and in order to turn this into some sort of expression where I can write it as a fraction, what I'm going to do is I'm going to take natural log of my limit, and that's going to be equal to the limit as x goes to 0 from the plus side of natural log x to the root x, just like so. And now I get to use the properties of log, and I can bring the square roots in front. So this is the same as the limit of, let's see, I get ln x square root x. Oops. And now I can turn this into a fraction, right? So this is the same as the limit of ln x divided by x to the minus a half, right? Because root x is power positive a half, but if I bring it in the denominator, I end up with x to the minus half. And now x goes to 0. X to the minus half is like 1 over x to the half, right? So that goes to infinity, and so does the log, right? Minus infinity. Now, if I apply L'Hopital's, that's infinity over infinity. What I end up with is I have to take the derivative of the top, so this is the limit of 1 over x on top divided by, bring down the exponent, x to the minus 3/2. Excellent. Now I have to keep manipulating this a little bit, right? So what I'll do is I'll now bring this on top with a positive exponent. So this is the limit as x goes to 0 from the plus side. I have negative 2 over 1 by taking the reciprocal of this times x to the positive 3/2, right, because I'm bringing this on top now, times 1 over x is x to the minus 1. So now I get to combine exponents finally, and this is the limit as x goes to 0 from the plus side, negative 2 over 1, x to the, well, 3/2 minus 1 is just 1/2, so this limit is just 0. So what I just found is that the natural log of my original limit that I'm trying to compute is 0. And the only way natural log of something is 0 is if that limit was 1 to begin with, because ln of 1 is 0. Okay, now for the final problem, I'm going to use a similar technique. So I'm going to let this be L, which is what I'm trying to solve for. And what I'll do is, again, I'll take natural log of both sides. So natural log of L is the limit of the natural log of x to the 1 over x. And I'll bring the 1 over x down in front. So this is the same as the limit of x going to infinity of ln x times 1 over x is just ln x over x, just like so. So the top goes to infinity, bottom goes to infinity. So that's the infinity over infinity L'Hopital case. So that means then that this is just the limit as x goes to infinity of derivative of the top is 1 over x divided by 1, and that is just, well, 1 over infinity, that's just 0. So the ln of my limit that I'm trying to compute is 0. That means L is equal to 1 again, just like before. So that's it for the worksheet.